Okay, so in this video we're going to look at one final way of assessing normality of a population by looking at a small sample. And this tool that we're going to learn in this video is called a normal quantile plot. It's actually a very handy tool that statisticians use all the time, and you're going to know how to do this in your calculator by the end of this video. You've also got at your disposal some of those other tools that we recently looked at, but you'll see that this one is another one that you can add to that list. So here's the example. It says, is the following sample of 9 test scores coming from an approximately normal population? So I hope to illustrate with this example a little bit of the background and theory of what's going on with a normal quantile plot. So the big question is our original population something that looks like this? And if it is, then when I'm selecting these 9 data points, I would be expecting those 9 data points to be coming from a range of places throughout this normal population. Now, given that there's 9 values, we could actually separate the normal distribution into 9 sections, or actually 10 sections, and we could separate it like this. We could say, let's separate it into the 10th percentile, then the 20th, 30th, 40th, 50th percentile, etc. 60th percentile, 70th, 80th, and then all the way up to the 90th percentile. And so if I was drawing 9 values from a normal population, I would expect those 9 values to come from a range similar to this. Now, this is kind of convenient in this question because I have 9 data points, and you can see I've got 9 percentiles listed here. And I've set it up that way to try to make this clear, because these can change in a lot of different questions. These are called quantiles, and it's the number of quantiles are entirely based upon how many data points that you have. But in this case, you can see that I've sorted the data. It's in order. And so if this is all coming from an approximately normal population, I would expect 65 to be relatively close to the 10th percentile. I would expect 68 to be relatively close to the 20th, 70 to be relatively close to the 30th, and so on. And so the big thing that we're going to do is we're going to say, is there a connection, or is there a relationship between these values and z-scores that correlate with the percentiles that I've written here? And so what we do is we take this information and we put it into data points. And each data point is going to be in the form a value, comma, z-score. And the value is just the number or the data point from the sample, and the z-score is the z-score for the particular percentile. Now, we're interested in, is there a correlation or not? If there is a correlation between these values and these percentiles or z-scores, then that would lead us to believe that, yeah, maybe our original population is approximately normal. So let me remind you that a z-score has a certain formula. And the formula for a z-score is a linear relationship between a value x and a z-score. And so that means when I plot all of these points that are in the form value, comma, z-score, I am interested in the correlation. I'm interested in do I have a relatively linear relationship between those value and the z-scores? And if you do, so if that correlation is linear, then we will be able to state that our original population is approximately normal. And so let's take a look by plugging this data into the calculator and seeing what we get. So just as we did this before, we're going to go into Stat Edit, and we may have to clear out a list. Remember, to clear a list, you just press Clear Enter, and we can enter 65, 68, 70, 72, 73, 77, 79, go 83 and 85. So there are the 9 data points. Now, as I do this in the calculator, I'm at the same time going to write the steps in the notes here. And so, we are going to, at first, I'll write down what we just did. So stat edit and enter your data. And now we're going to go into the stat plot menu, which is something that we've gone to numerous times in this class. So we're going to say second y equals. That takes you into the stat plot menu. And we are going to turn plot 1 on. And you see a lot of the tools that we've used throughout the class. The normal quantile plot is the very last picture. So if we go all the way to the end and we press enter, you can see it changes to data list is L1, and you don't need to worry about data axis. We could just leave that on X, and that is the normal quantile plot. So second y equals, I will say turn the plot on, and in addition to turning the plot on, select the normal quantile plot, which is the last picture. Okay. Now, whenever we leave this menu, what we've always done in this class is we've always pressed zoom, and then we go down to number 9, which is zoom stat, and that's what I'm going to do next. So I go to zoom stat, and let's see what happens here. So if we, you don't even have to scroll down to number 9, you can just type in the number 9. And so looking at that plot, do you see that that looks very linear? When I observe this, I see, it's not a perfect line, but at the same time, there's a little bit of a bump there. There is the points, for the most part, do follow that very linear pattern. When you're doing homework involving this, one of the useful tools in the calculator is actually pressing the trace button. And so consider pressing the trace button to see the specific points. So if I press trace, it tells me that point is x equals 65 and y equals negative 1.59. So remember, this is our data point, and this is the z-score for the 10th percentile. And then if you just arrow over, you see all of those data points. So this particular data point was 70, and the z-score for that is negative 0.6. So that's why you see this horizontal line in the middle, because z-scores are on your vertical axis, so you have negative z-scores and then you have your positive z-scores up here. But the only thing that you really need to look at in this is if you see a relatively linear pattern, then you say yes, there is that strong correlation between our data values and our percentiles, and so we would conclude that that would imply our original population is approximately normal. And like I said, when you enter this into the homework, make sure that you use this trace button and arrow over from point to point, because that way you can enter these specific values in. Now let me show you what would happen if for some reason we had a normal quantile plot that did not imply the original population was approximately normal. And so what I can do is I can actually create some skewness in my sample by just using the same data that I have right now, and I'm just going to add a bunch of values on the low end. Now this isn't something you're ever going to do, but I'm just trying to illustrate a point here. So let's just pretend for a minute that we had a bunch of 62s that were also part of our sample. And so the only way that this would typically happen is if the original population was maybe skewed a little bit in that direction. So if we did zoom 9 now, look at what happens to that normal quantile plot. So instead of having that nice linear pattern that we had before, now we've got this end of it that kind of indicates that there was some sort of skewness or some type of a problem in the original population. Maybe not necessarily a problem, but it's indicative that the original population was not approximately normal. So a lot of times when you conclude that the normal quantile plot is not indicative of a sample coming from an approximately normal population, you're going to see things like this. You'll see little things at the end usually, or you'll see more curvature in the middle and things like that. But a lot of times it's at the end where you'll see funny behavior going on like that. So, so this is the idea of a normal quantile plot.